Hey YouTube, it's Dimitri, and today we're going to do a response video somewhat because we did a video last week on just what is AUC, which is area under the curve, and how do we use it in credit modeling. I'm trying to show you guys just a different metric that many of you probably haven't seen on the quantitative finance side. A lot more common in the machine learning space. If you're taking machine learning, you've probably seen it as well. But just trying to give you some light and definition on how we use it in practice in the industry here. And it sparked a bunch of questions and people wanting some opinions on things, which was fine. And so I thought I would dive in a little bit differently on this because I am not a machine learning, obsessed person. I think math, stats, machine learning, AI, it's all just math. And so today I'm going to just give you a little bit of more of my perspective on some of these ideas, some of these thoughts, why I tend to use AUC, why the industry tends to use AUC. Machine learning space will typically use like an F1 score, which we'll talk about here in a second. And somebody else mentioned like a Breer score. You can use a Breer score for this. It's an accuracy metric. Again, I'm going to tell you this from a model development perspective, which is I don't care about accuracy. I really don't. It sounds very odd, but I'll explain why business model developers tend not to care about it, whereas the end user is going to care about it obsessively, and that's going to be a really frustrating part between a model developer and a user here. Now, accuracy is important, right? That is the goal of the model, is to predict something, but accuracy in itself, I'm just not a big fan of it. I don't think it really matters too much, which I know sounds odd to people, but model robustness is probably the gold standard we're striving for in most cases. I will get to that. So let's go through a few definitions here. We talked about last week, we talked about the confusion matrix. So the confusion matrix looks something like you have the actuals on top and you're going to have the predictions on the other side of this matrix. And you're going to have, so in credit modeling, we say goods and bads. Bad is what we are predicting, which is 1. Good means somebody did not default on a loan, and so the value is going to be 0. Anyways, and you're going to have bad and good and bad and good. And you have this matrix here. And what we're going to say is this is going to be called TP, which is true positives. We're going to have false positives. We're going to have false negatives down here, and we're going to have true negatives. So again, this bad is what we call positive. 0 or goods is what we call negative. So all this is saying, for example, like true negatives means that we predicted negative and the actual is negative, and therefore it was true. So it's truly a negative for both of these. False means that in this case, right, false negative down here, and it just means we falsely predicted that negative account here. So we predicted that it was good when in reality it was going to be bad here. So this is a confusion matrix. If you want more details on this video is not intended to go through this. You can go look at other videos. StatQuest has an amazing video. Shout out to him. And you can also go look at the other videos I've done as well. I'll link, that one above. But essentially, this is what we call the confusion matrix. Now, last week, we also talked about what's called AUC. So AUC, we had what's called the true positive rate. This is also known as sensitivity or recall. And we plot this out against the false positive rate, which is also 1 minus specificity. Say that 10 times. And essentially you have this 45-degree angle, which means essentially as we move a threshold across this. So let me get into this real quick. You have something that you're going to predict here. You have a bunch of dots, right? These are 1, this is 0, so this is bad, this is good. And you're using logistic regression or a decision tree or any sort of model that's trying to split these two classifications. And you're going to have some sort of threshold here that you're going to move around. And it looks like this, and you can move it this way. Anyways, you can move this threshold around. You can pick what you want, and you can use that and try to measure different sort of metrics here, which I'll talk about here in a second. But AUC is what we talked about last week, and that's area under the curve here. This curve is going to be the true positive rate and the false positive rate, where we move the threshold across these values down here. So we move this and we slowly move it up, and we look at the score. So this is going to be a prediction score. So we're predicting a value between 0 and 1, so it'll be a decimal. And as we move that across as a threshold here, we calculate out a bunch of these different metrics, which I'm going to show you here in a second, based on the number of goods and bads, or zeros and ones. And then we plot this out over here. And then to get AUC, which is area under the curve, we literally just sum up the area under the curve. So this goes from 0 to 1. This goes from 0 to 1. The area of this entire box is equal to 1. That's perfect prediction here. Now, the area under here, for example, in most cases, let's say this is like, 0.75. So, the area under that curve is going to be 7.5 here. Now, let me talk a little bit about these metrics, and I'll put names to them real quick. So we talked about sensitivity, which is also called recall, which drives me insane. There's two names for this, but the true positive rate, or the sensitivity, or the recall is going to be true positives divided by true positives plus the false negatives. So you would pick some sort of threshold. You would go up here to this matrix after you select the threshold, and then you would basically count the true positives. You'd put them down here in this model, and then you'd carry the same number here. And then you'd look back at the table, you'd pick the false negatives, you'd put it here, and you calculate sensitivity. And I don't know, let's say this is 0.81, just making stuff up here. But you would look at that. And then there's our other measures as well, as we talked about. There's something called specificity. Can't even say this. And this is going to be the true negatives divided by the true negatives plus the false positives. And you can make some number up for this. I don't know, 0.72. I don't know, make something up. And then finally, we're going to have a third one called precision. And this is going to be equal to true positives divided by true positives plus false positives. So it's slightly different from sensitivity here. And we can make up some number for this. I don't know, 0.83. Okay, so there are all these different metrics here, and they all tell you different things here. We typically choose specificity if essentially, correctly identifying the zeros in the case is more important. So in our loan case, we think about, we need to get these zeros, these negatives. That's the most important thing. We would use specificity. Again, it's kind of important, right? Because in a model, I want to predict the bads. That's what I really care about. I want to avoid the bads. But also, I don't want to, be stupid and put a threshold way up here and say, hey, I have to predict that's like a 99% bad possibility. And then I'm just going to, reject all those loans because I'm going to be missing all this volume here. And we're a business. We're trying to make money. Also, from a fairness perspective, right, there's a lot of people under that 99%, so 0 to 99, that are going to be great customers that need loans for cars and mortgages and other products here. So, there's a moral aspect to this as well here. So, that's we're trying to balance these different sorts of calculations here. Now, you choose sensitivity if correctly identifying the bads is the most important aspect. So you could look at that and you could say, okay, sensitivity, this is the metric I really care about because I'm really concerned about, those true positives. And the true positives, if you're concerned, is right here. It's identifying those bads. That's what I really care about, right? I really care about getting rid of the bad loans. And you do, but there's a volume trade-off here in the loan market here, in the credit markets here. So as I'm kind of hinting at and talking about, I hope you realize, if you have too strict of a threshold, you're not going to get enough customers through the door. You're not going to make enough profit. Your losses will be almost zero. You'll be making nothing but money. But you'll be making nothing but money on $100,000 in business for the year. To put that in perspective, and I worked at one of the large firms, we were generating $60 billion in loans and auto loans. So when you think about that, right, I would much rather do $60 billion in loans and have a loss rate of 20 to 25%. Again, there are other factors and things for if you can securitize loans, those loss rates, cumulative net loss, and all that sort of thing. Whole other business side of this. Not going to get into this. But those sorts of business decisions also help impact why we're selecting the thresholds that we select here. And I want to hit that home here. Statistics and data science, machine learning, optimization does not matter that much in the real business world, right? You need to understand it. You need to understand where the thresholds are, where the optimal position is. But the business unit is going to be using the model. They're going to have insights like volume and loss rate trade-offs, and they're going to tell you it's critical. So shed a little light on this. If your loss rates are too high, you can't securitize those products and sell them. Banks make money by making loans, and then they securitize those loans and sell them to the public, or to investor groups most likely, typically as hedge funds and big investment firms, whatnot. And then those investment funds are wanting exposure to these sorts of markets. They're diversifying. It's a great strategy, even in retirement. Looking at this thing from a consumer perspective, I would want to diversify across multiple sorts of asset classes, including auto and mortgage and credit card portfolios and a bunch of other things that are harder to get exposure to unless you went through the securitization process. Now, the bank wants to do the securitization because they need to get the dollars back on their account, their books, to make more loans. Banks are specialists at originating loans, engineering financial products here. They're not specialists in just sitting there and holding cash forever and making some sort of long-term investment decision. They're really getting paid for the transactional ability to generate paper, as we call it, but generating loans of a specific credit quality and then having marketability to sell those loans into the marketplace here. So the business side of this is going to play into this. Now, understanding all this is critical because you need to educate the business and explain it and help them through all this. But often you're not going to pick the optimal statistical or mathematical approach because there are other business considerations that will play into this puzzle here. So getting back to this now, right? AUC is an amazing metric because it's not one of these three metrics down here. Again, it's using 1 minus the specificity, which is going to be this. So 1 minus this. Is actually going to be this false positive rate. And then this recall or sensitivity is going to be the true positive rate. And that's going to go up here. So we're kind of looking at the balance here. We're trying to see both halves. But more importantly, why AUC is reviewed, why it is looked at, why it is checked, is because we also have the original line from the model. I'm going to call it dev. You're going to probably call it training in the machine learning world. And then we do a separate back test, essentially, in the finance terms, which is going to be your out of time data. You have to split on time. And you're going to see this other curve, and you're going to see some sort of shape, and it's different. Again, I'm not just concerned with my AUC metric. I'm also concerned looking at and reading the chart to see where the deterioration in the model is. And so this ROC curve and the AUC chart, like this whole ROC chart here with the AUC baked into this, I'm looking to see how robust the model is. So again, I want to look at, these metrics down here, which we talked about, but I don't just care about one threshold. I want to see the robustness of the model. How good is this model going to hold under different scenarios? Now, machine learning is notorious for overfitting. It's a whole other topic for this. And the vast majority of models built in the machine learning space are just garbage because you don't have a lot of qualified people. And there are some amazing people at firms, tech and finance and banking as well, that are super qualified and are using these. I mean, we use Light GBM right now at work. We use a bunch of different decision trees. But in general, right, you're concerned about the entire framework. You're concerned about the model lasting over a longer period here. So when we're making loans in the auto space, right, typical loan is like between 4 and 7 years. Some crazy people are doing 8-year loans. This model has to make a prediction today, and it has to be right for a full 6-year period here. And maybe an average life of a loan is, 28 months or something, 30 months. But it has to be correct through these sorts of longer period terms here. So robustness and accuracy in the model are these trade-offs that we're talking about. But I want the model to be stable and predictive and valuable for a long period of time. Now, on the development, on the cost, on the management side, I'm paying $100,000+ per person to build a model. In a standard bank, when I was in banking practice, you typically it'd take 3 months to build a model. So one employee can build 4 models a year. Average starting salary, a lot of the banks when I was doing this, is typically around 80,000 non-New York salaries. You want to get into New York, you can bump to like 100, 110. But like Dallas area, Charlotte, where we're doing credit modeling, 80,000 is typically the starting salary. Again, there are pros and cons in different salaries. But then you get up into like the mid-level vice president modelers, you're probably looking at 140 to 180 to pay someone to build a model. So imagine they build 4 models a year, and imagine every year they fail and you have to rebuild those models every single year. That's costing money. Having a robust model, you could extend out to 2 years. You're getting double your value on your employees in your modeling. Your risk practices are better. Your business decisioning is better. There's less communication, less meetings. There's a whole bunch of cost involved in redoing models here. So again, looking at this from a business side is also a critical piece here. And so when we look at this ROC and the AUC together here, we're looking at the curves and we're looking to see where the deterioration is. So if you look at the green line, which is the dev, and the blue line, you can see here for predictions that are going to be on the lower side, we're seeing that if we do the out of time sample here, so typically it's about a year, when the data is changing and the markets are moving, the lower predictions are becoming less accurate because it is becoming closer to this 45-degree line here. Now you see on the upper end of this, so this is the higher risk, it's the higher probability in this example, we're getting more accurate in the riskier tail of this. So in this case, when you see these curves cross, like in this example here, the model's deteriorating, or maybe it's not even deteriorating, it seems to be handling quite well. Let's say AUC is 0.74. 0.74 is less than 0.75, but they're almost the exact same value. And when we look at these two curves, it's getting even more accurate in the high risk loans, and it's getting slightly less accurate over here in the good accounts. And I don't really care about that. I really care about this high risk area up here. So if we are increasing it out of time, it is stellar and amazing. So just to summarize why we look at these, I'm looking at a whole model spectrum here. It's not even like somebody asked about like, well, what if I just not select, like I just want to select a threshold, I just want to be done with it. Well, if that's your problem, that's like what you're solving, that's fine. But again, how does the model perform across everybody against all thresholds, right? I want to see how good the model is on the inside out. Now, other pieces I'm going to throw into here because I didn't talk about these in the last video. One, we're going to talk about data, and weight of evidence binning is something I have not made a video on. Maybe I'll make one in the future. Most variables you will force into a monotonic relationship. In simple terms, essentially, if you have your dependent variable, whatever you're modeling, y, and you have x is what's your input, your independent variable here, you have some sort of relationship, and it will have unique data points, and it will handle this. Weight of evidence is great also for handling missing values, and also for handling outliers. It is not a silver bullet. It doesn't solve all your problems. But essentially, then when you go to do the estimation on these, you end up with some sort of regression here. And again, it's monotonic. It doesn't have to be linear, but you're forcing the direction. So when I talk to the business, I can say, I don't know, let's say something simple. Like when there's something called LTV, which is loan to value. And this is really like a risk, it's like a risk metric. But anyways, as you could say as the prediction here of default, so as the probability of default increases, I would also expect that your LTV would increase. Now, if you had some sort of relationship using a decision tree, for example, and it has some sort of hump or nonlinear shape to it like this, and let's say, this is LTV, you're bad. It's a wrong. The model's invalid. So the binning part of this process, we review all the relationships, the coefficient directions. In a decision tree, again, we use weight of evidence, even in decision trees often, not always, but often, to help force the relationship so we can guarantee a logical understanding of the model and that the model is doing what we expect it to do. The other piece here is if you're going to use logistic, you're going to be looking at the p-values of the variables involved. You're going to be looking at VIF. This is variance inflation factor. So variance inflation factor basically measures multicollinearity within the model, which just means if you have two variables that are almost the exact same and you're putting them into the same model, the coefficient estimates are going to be invalid because the model does not know, nor mathematically can you figure out what is the correct estimate for them, because it's the same thing. So when you're like double counting, think of it that way. In a model, you're double counting. And so when you're double counting in regression models, the models don't work very well. The coefficients are invalid, and often we will judge the coefficients, as I kind of talked about up here, looking at like the signs of them and the directions and all that. So that's important. P-values, again, is a statistical test because we want to see, is the variable statistically significant? Like, do we actually think, given the data, that it is driving the prediction? We care about causality here. And as I kind of hinted at, right, the business is going to look at this. They're going to complain. They're going to say, hey, the model's not working. I want this, that, and the other. And I think, this customer should have got a better price. And they're always going to be doing that. And that's fine, right? You want some challenge and some feedback on that. But at the same time, you need to be able to explain that and justify that. And that's why we typically use logistic regression, or even we force smaller decision trees because you can go through and break out populations and explain why customers got scored the way they did. Now that helps the business. There are also regulatory requirements for anyone originating loans, and you have to be able to justify and explain why a customer got a score they got. So all this matters here. So there's all this extra work that goes into the modeling before we even get to the final model, and before we start, plotting this out and getting our AUC and looking at our ROC curve here. But trying to get this in a robust framework, right? This is why we care. Okay, so ROC and the AUC as well. Again, it's a single metric, but we're looking at that shape. We're looking at the dynamics. We're looking at the other curve. I mean, if it's coming down here and the model's deteriorating when we have like out of time, it's a garbage model. You overfit it. It doesn't work. Something else is wrong. So then you'd go back to the drawing board and kind of look at all these different metrics here. Okay, so one last thing in this video here, we're gonna just talk about F1 score, and I'm gonna throw in there I'm not gonna talk about it too much, but I'll throw it in here as well. You can use what's called a Breer score, Breer skill score. It's an accuracy metrics, and yes, it is statistically, I think it's a stats metric. So that's cool. Like, if you want to use that, you can start to use that. Again, we just don't tend to use them in practice. I might look into it a little more and use it. It's just not something I'm like super comfortable with, and I've never really used them in the past, to be honest with you guys. So interesting approach, another something you can look at. But again, it's not going to replace the ROC because I'm wanting to see the curve and the shape and the difference between your development and your out-of-time data here. So again, it's something else you can add into the mix. F1 scores are something else I have seen the machine learning community use. I've seen developers use it. I don't really care too much about it. It's more of I think it's better to be used as a decisioning tool for selecting a threshold, which I'll show you here in a second. So F1 score is going to be the harmonic average between precision and recall. So that was that trade-off we talked about, right? And to give you guys this in simple terms, precision is going to be true positives over true positives plus false positives. You can think about having some sort of space. You have some sort of threshold here, and we're only going to look at the threshold that we're cutting off at. So let's say we're just cutting off here and say this is 0 to 1. And in this case, this is going to be the threshold of loans. We're going to accept everything that's going to be left of this. And so we look and see, okay, how many did we get correct? We got, okay, let's say 1, 2, 3, 4 of these correct. And we got, I don't know, 2 of these, incorrect here. So we would look at this and say, okay, we've got 4 out of 6 of this. This is like a 40% precision. I believe this is how this goes through. Bear with me here. I'm doing this by the seat of my pants here. But again, so you're only looking at the threshold that you're cutting off on. So the other side is going to be recall. That's what we're looking at. And this is going to be the true positive over the true positive plus the false negative. So looking at a sort of chart here as well, we're looking at this. We have some sort of threshold. We're going to be looking at bads here. So bads is what I care about. I want to predict these sorts of bads here. But I'm going to look at them on both sides. So I'm going to say, okay, I have 1, 2, 3 bads on this side, and I've got 1, 2, 3, 4, 5, 6 on this side. Now, again, trying to think through how I said this before. We care about this in the sense of the bads. But in this case, what you would look at is you'd say, okay, we correctly identified 1, 2, 3, 4, 5, 6 of these bads. So we'd 6, and there's 7, 8, there's 9 of these. So it's like 66%. I could have this backwards based on the threshold. But essentially recall is looking at the full population, and you're looking at the bads and saying, okay, how many are bad over the full population, and how many of these do we get correct? So in this case, right, I'm saying these ones are the correct ones, the true positives. And then when we do precision up here, we're looking at, I drew this threshold. I'm looking at all the loans under this threshold, or probably more correctly, this would probably be on the other side of this because you're looking at the bads. I know it's confused me a little bit because the loans we make that are going to be the good ones. Anyways, but we're predicting the bads. But you'd calculate these up based on the threshold itself, not on the full population. So you'd say, okay, identified these as bads. There's 1, 2, 3. There's 4 bads. There was 6 in total. And so you'd say it's 40% here. The F1 score now is going to take a harmonic mean. And the equation for this is just going to be 2 times the true positive divided by 2 times the true positive plus the false positive plus the false negative here. And so the F1 score is great because it gives you this sort of balance here. Now, again, you can plot these things out, right? I mean, this is the cool thing about, modern day era here. But essentially you're going to have like the percentage of predicted positives. So in our case, this is bads. And it's going to have some sort of F1 score that's going to look like this. And you're going to have some sort of peak. And essentially, if you want to pick, you know, the maximum F1 score might be like here. And then if you wanted to plot something else, so this is a F1 score, you can plot something else like this. And this green line is going to be accuracy. And it might be slightly over here. And of course, this is 0. This is 1. That's what we're predicting. And you can use F1 score to select, like this case here, right? The blue line selects the peak, the optimal score for that. You could use that as a strategic decision. You could make that as a recommendation to the business. The business could go through, or you could go through as a decision scientist, which is more like an analyst, and look at these sorts of strategic decisions, like pricing teams, and figure out, you know, hey, this is where the optimal threshold is. This is what we recommend. But then you could go through and run like volume estimates, and you can run pricing estimates, market share. So volume is capturing market share. It's how many loans you're going to be capturing out of those. Yeah, lots of people apply, and then you end up rejecting the loans, or they reject you. Like they go, oh, you know, you gave me this price. Like that's not that great of a deal. I'm going to go out, you know, to another bank or another firm and get a better deal. So you have to consider all these other business practices, but this is a great way to do that. You can also look at these sorts of charts and scores, and again, you could get creative, and you could do, you know, your development, and you could add an out of time, and you could look and see how the model shifting and try to get some sort of a robust, great decision with a great model. So F1 score is another really cool metric here. So you guys can use. I'm recommending go look at all these things, look these things up, do more research. This video is definitely short and just trying to get at the points of why AUC and ROC curves are used. F1 score is another one, and the Brier score, or the Brier skill score, is something else that you could use as well, right? They're all kind of things to look at and optimize on. I hope though for the takeaway of this video, you realize we should not be looking at just one thing, like just precision or just recall. You need to have dynamics and make better decisions on that. And that's why it seems kind of short-sighted in the last video, because I quickly ran through AUC. But AUC is just one view. So you can use F1 scores or Brier skill score, or something else, and you can kind of look at this from different perspectives and then think about what is it actually calculating, what do we care about most, and make that decision. Again, AUC just happens to be in the ROC curve, are just the most common things that have been historically used. So most firms, most funds use them, and they're understood well just because you get used to using the same tool over time. But there are other skills and tools out there, there are charts you can use and make justifications and help you make better decisions. So anyways, thanks for watching. Thanks for listening. And as always, until next time.